Have you ever wondered what really happens when you click a link? You type in a website, hit enter, and poof, the page appears. But behind that simple action is a mind-bogglingly complex dance of data sipping across the globe. It feels like magic, but it's actually a beautiful system of rules and logic. Today, we're going to demystify one of the most important parts of this process, the transport layer. Welcome to our digital world, built one layer at a time. Imagine the entire internet is a massive, bustling planet. On this planet, every computer, server, and phone has a unique address, kind of like a street address for a house. This is its IP address. When your computer wants to talk to a server, say to watch a video, it needs to send a package of data to that server's IP address. But here's the tricky part. A server isn't just one big open room. It's more like a giant apartment building, running hundreds of different applications at once. It might be hosting a website, handling emails, streaming videos, and managing a game server all at the same time. If you just send a package to the building's main address, how does it know which apartment, which specific application it's for? This is where the transport layer and its secret weapon, ports, come into play. Think of a port as the apartment number. When your computer sends a request to watch a video, it doesn't just send it to the server's IP address. It sends it to the IP address asterisk and asterisk, a specific port number associated with the video streaming service. For example, web traffic usually goes to port 80 or 443. This way, the server's operating system acts like a doorman, looking at the port number on the incoming package and delivering it to the correct application's doorstep. So we have IP addresses for the where and ports for the who. But how does the data actually get there reliably? This brings us to the core job of the transport layer. It's not just about addressing, it's about transportation. The two most famous couriers in this business are TCP and UDP. Let's start with TCP, which stands for Transmission Control Protocol. Think of TCP as the premium white glove delivery service. It's obsessed with reliability. When you send a large file like a photo, it can't be sent in one giant chunk. It has to be broken down into smaller, manageable packets. TCP takes your photo, carefully chops it into numbered pieces, and sends them off. But it doesn't just hope for the best. For every single packet it sends, it waits for an acknowledgement, a little "got it" message from the receiver. If a packet gets lost somewhere on the internet superhighway, or if it arrives corrupted, the receiver will notice because the numbers won't add up. It will then tell the sender, "Hey, I'm missing packet number 73, and TCP will dutifully send that specific packet again. It also makes sure all the packets are reassembled in the correct order on the other end, so your photo looks exactly as it should. This three-way handshake at the beginning of a connection. Can you hear me? Yes, I can hear you. Okay, let's talk. Ensures both sides are ready. This process is perfect for things like loading a web page or downloading a file where every single bit of data is crucial. But what if you don't need that level of perfection? What if speed is more important than a few dropped bits? That's where UDP, the User Datagram Protocol, comes in. UDP is the express courier who just throws the packages over the fence and runs. There's no connection setup, no acknowledgements, no resending lost packets. It's fire and forget. It's fast, lightweight, and efficient. You might be thinking, why would anyone use such a sloppy service? Well, it's perfect for real-time applications like video calls or online gaming. On a video call, if you miss a tiny fraction of a second of audio, it's not a big deal. Your brain just fills in the gap. It's much better to have a continuous, real-time stream with tiny imperfections than to have the whole video pause while it waits for a lost packet to be resent. With UDP, the stream just keeps flowing. The game doesn't stop because one packet with your character's position got lost. It just gets the next update a millisecond later. It prioritizes low latency over perfect accuracy. So the transport layer gives us a choice: the reliable but slower TCP, or the fast but less reliable UDP. The application gets to choose which service it needs. Now let's zoom out and see how this all fits into the bigger picture. This concept is called layering. Computer networking is designed like a stack of services, where each layer has a specific job and only talks to the layers directly above and below it. At the very bottom, you have the physical layer, the actual wires, fiber optic cables, and radio waves that carry the signals. Above that is the data link layer, which handles communication between devices on the same local network, like your computer and your Wi-Fi router. Then comes the network layer, where the IP address lives. Its job is global routing. It's like the International Postal Service, figuring out the best path to get a packet from a city in one country to a city in another. It doesn't care about what's inside the packet or whether it arrives safely. Its only job is to get it from the source IP address to the destination IP address, hop by hop across the vast internet. Sitting right on top of the network layer is our hero, the transport layer. It takes the big data streams from the applications above it and breaks them into packets for the network layer below. When data arrives, it takes the packets from the network layer and reassembles them for the correct application. It acts as the bridge, adding the port numbers for specific applications and providing the choice between TCP's reliability and UDP's speed. It's the building security guard who receives packages from the city's courier and makes sure they get to the right apartments, either by getting a signature or just leaving it at the door. Finally, at the very top is the application layer. This is the layer we interact with directly: our web browser, our email client, our game. The application layer speaks its own languages, like HTTP for web pages. It doesn't need to know anything about IP addresses, ports, or how data is chopped up. It just says, "Hey, transport layer, please send this message to this server and let me know when you get a response." Each layer trusts the layer below it to do its job. This separation is genius. It means you can innovate on one layer without breaking the others. We can invent new Wi-Fi technologies at the physical layer, and our web browsers at the application layer will still work just fine. A web developer building a cool new website doesn't need to be an expert in how routers work. They just need to know how to speak HTTP. The network layer handles routing. The transport layer handles reliable or speedy delivery to the right application, and the application layer handles the actual content and logic. This brings us to a fascinating question. When you open a web page, what exactly are the browser and the server saying to each other? The browser, an application, uses HTTP, the language of the web. It crafts a message that says something like, "Get me the main page from this website." It hands this message to the transport layer. Since a web page needs to be perfect, it chooses TP. TCP wraps the HTTP message in its own reliable envelope, adds the destination port number, usually 443 for a secure site, and breaks it into numbered packets. It then hands these packets to the network layer, which puts the server's IP address on them and sends them on their way across the internet. On the other side, the process happens in reverse. The server's network layer receives the packets. Its transport layer reassembles them using TCP, checks that everything is there, and delivers the original GET message to the web server application listening on port 443. The web server then finds the page, writes an HTTP response, and sends it back through the exact same layered process. This intricate layered dance is what makes our connected world possible. It has a system of trust and specialization that allows for incredible complexity to be managed with elegant simplicity. So next time you click a link, take a moment to appreciate the silent, coordinated effort of all these layers working together. From the application on your screen to the transport layer's careful delivery, all just to bring that page to you in a fraction of a second. Thanks for diving deep into the world of networking with us today. If you enjoyed this journey through the layers of the internet, be sure to like this video and subscribe for more explanations of the technology that shapes our world. See you next time.